like homework A, anyone wrote anything, I give at least half the grade. So there is nothing different.
Yeah, it's almost started.
I mean, well,
Frank, what was the homework you got from your mom?
Like 5, 6.
All right, guys, let's settle down and get started. I know it's very exciting to get your homework back. All right, guys, let's settle down. Please wait until after class to pick up your homeworks. One very important announcement. Munir here is the grader. If you haven't already turned in your homework, please turn it in, because if he doesn't get it now, it's pretty much gone. Munir, you're leaving on... Okay, please leave the homeworks alone for now. So if you don't, if one of your friends isn't here and they want to turn in the homework, they should contact Munir directly to arrange for a pickup. And it's going to be in the next. It's basically tomorrow. It's got to be tomorrow, because Munir is leaving town. Okay. All right, so today's lecture is obviously the last lecture. Al has an announcement.
Okay, review session. Tuesday or Saturday? Those are your choices. Saturday. Tuesday, so a full week in advance? No, Saturday. Tuesday. Wait, next Tuesday. How many want Saturday?
How many want both?
It'll be on Saturday in the middle of the day. I'm sorry, on Tuesday.
All right, we'll put up the important announcements on the webpage. So in the next couple weeks, check the webpage for announcements about review session and also about extra office hours. I'll be holding office hours during the break, and I'll put up the hours. And if you need to see me outside of those hours, if they conflict, send me an email. We'll make an appointment. Okay. Any other questions? All right. So the homework you turned in today is your last graded homework. There'll be another mini homework assignment that will basically not be due. It'll be for your own good. Other than that, the graduate students have the project, and then it's the final. Okay. So any questions about any of that stuff? Yes. The project will be due basically the day of the exam. So you can bring the project to the exam. I'll probably spend the exam looking through the projects. I trust you guys won't cheat. But if you want to turn it in earlier and get it off your hands, you can do that as well. All right. Any other questions? You can send me a soft copy earlier, but if you bring a hard copy to the exam, because I want to be able to go through them. Okay. Okay. So let's switch back to the lecture, and let me basically, can we use the computer? All right. So this is where we left off last lecture. Basically, we were looking at a Class A amplifier, and we talked about how the parasitics of this transistor, for instance, could get absorbed in this drain inductance or collector inductance instead of using a choke. And we have a matching network to transform this impedance, which is probably 50 ohms, to some convenient value that we like to drive. That convenient value may be actually quite a bit lower than 50 ohms, depending on how much power you want to give. The way to think about it is the power that is available at the collector of this device is V squared over 2R, where R is basically the load impedance, the optimum load impedance that determines how much power you're driving. So V is like, let's say VCC, and let's say you're a 1 volt supply, V squared is 1. So you can put out half a watt per ohm. So if you do in fact want to put out half a watt, that means the impedance at this node has to be 1 ohm, right? That means you have to transform 50 ohms down to 1 ohm, which is a huge matching ratio, okay? Now, that's actually not the complete story. The complete story should also take into account the package parasitics. So the package parasitics, we talked about this when we discussed the LNA, but let's just review. Typically, you design this chip, as I've shown here, and you put it into a package, and you have to have bond wires that go from the chip to your package. So these would be like metal leads in your package, and this is the bond wire. And now you can see that because of the macroscopic dimension of this package, that there's actually going to be quite a bit of inductance associated with this package and also with these bond wires. So these things turn out to be very important when you design your PA. Okay, why is that? Well, on the collector side, it's not much of an issue because, you know, initially we assumed we had a choke, so you put more inductance in series with the choke, it's no big deal. If in fact you are using this inductor to resonate out the cap, you might actually take advantage of that inductance because that's a high quality inductor. The bond wires and package leads, actually inductance is quality factors on the order of 20, 30, or even better, depending on the frequency. So you could use that inductance to your advantage on the collector side. On the emitter side, though, it's actually a disaster because if you have current going through this inductor, it will involve a voltage swing, right? And that voltage swing subtracts out from the voltage swing that's available for the load. So this is actually a big problem. Remember when we calculated the voltage swing, we needed to calculate VCC minus VCE sat of this device. So let's switch over here. So the available voltage swing to the, you know, let's say we don't have any inductance. So in that case, the voltage here can go as low as VCE sat and as high as 2 VCC, right? And so then the voltage swing would be at best VCC minus VCE sat divided by 2. Okay? Now if I introduce an inductor here, the lowest voltage I can go has to take into account the voltage drop across this inductor. And for simplicity, let's ignore the phase of this voltage and say that the voltage across this inductor is simply j omega LE, this is LE, times the I swing, absolute value. Okay? So this, in a very simple way, is subtracting out from the lowest voltage that you can obtain. So now a pessimistic estimate for the swing is VCC minus VCE sat minus VL divided by 2. Okay? Now how bad is VL? Well, let's just take an extreme example to give us a sense for how bad it could be. Let's assume that L is 1 nanohenry, LE. That's not actually an atypical value of inductance in a package, in a normal package. All right, and let's say that the current is 1 amp. Again, that's not an atypical value of the current if you're designing a watt level cellular kind of power amplifier. Okay? And let's say that the frequency of operation is 1 gigahertz. Then omega naught L I swing is 2 pi times 10 to the 9 times 10 to the minus 9, that's the 1 nanohenry, times 1 amp, or 2 pi volts. That's a large voltage, right? That's about 6.28 volts. That means that my supply voltage better be larger than this, right? And in fact, the way that, if we look back to the equation that we derived, the efficiency is 1/2 normalized voltage times normalized current, right? So because my normalized voltage now, V, which is the swing divided by VCC, is gone down with a fraction of VCC, I better make my VCC much larger than 6.2 volts, 6.3 volts, for this to actually be a negligible impact, right? So if I had, let's say, a 10 volt supply, 60% of my swing's already, well, I should take twice that, so 30% of my swing is already eaten up by this guy. And so it's going to hurt my efficiency considerably. So this is why, in general, we prefer high breakdown devices. In other words, a device that can handle a very large voltage supply, because then I could use a very large voltage here, let's say 100 volts, and that means that the current goes way down for a fixed amount of power. And then this voltage swing has a much less impact, because not only has I gone down, but VCC has gone up, and so the overall fractional drop is much less. Okay? But if I put 100 volts here, that means a device has to be able to handle 200 volts or better for a Class A operation. Okay? Questions or comments? Yes, David.
You tune out the bottom inductor?
No, it's actually something you have to live with. It's something that the reason is that this, if you look at the external load is referenced to the system ground, right? And this is your chip ground inside here. So for instance, if I use a bypass capacitor, you might think that's going to solve the problem. But the current from this transistor actually has to go off chip and come back on chip. So if you guys can figure out a way to avoid this problem, that would be great. That would be really nice. There are ways of somewhat getting around this. If you have a balanced load, you could force the current to actually go through this path if you have a fully balanced load. And if you can do that, then you avoid going through this extra bond wire. And now the bond wires are here. And you could actually make these bond wires part of your matching network. So that's a partial solution, but it requires a balanced load or a floating load. Okay, let's get back to the slides. Well, one way to solve this problem is with money, right? Money can solve many problems in life. And advanced packaging technologies exist that give you very low inductance. One is flip chip packaging. So flip chip packaging, you take your chip, and instead of using bond wires, you flip it. You put bumps on it. These are little solder bumps. You flip it onto a high-performance package that has very low inductance to ground, and then you basically put this in the oven and cook it a little bit, and you have yourself very low inductance to ground, on the order of tens to hundreds of picohenries. So a factor of 10 to 100 less inductance than you would get from bond wires. You might say, well, why not just use multiple bond wires, right? So let's go back to the paper. So, instead of using one bond wire, maybe I can use multiple bond wires. Let's say 3 bond wires. Won't that cut the inductance by a factor of 3? Any comments? Any guesses? Right, 3 inductors in parallel, you get third the inductance. Why not?
Did you get mutual coupling between them?
That's right, they're mutually coupled. So because these things are mutually coupled, let's call this L1, L2, L3. So this would be L23, this would be M12, this would be M13. What you find actually is in the limit that they're perfectly coupled, then the inductance doesn't decrease at all. right? Because the mutual coupling is on the, depending on how close these bond wires are from each other, how close the pins are from each other, could be anywhere from 0.2 to 0.5, 0.6. So the inductance does go down, but not linearly with the number of bond wires. So there is a point of diminishing returns. You put down a bunch of bond wires, and you reduce that inductance, but you can't dedicate all the pins of your chip to the ground. You have to have other connections as well. All right? So that's why we have to use these advanced packages. Back to the slide. We can see here another option is, this is kind of, I would call, somewhat of the poor man's option of getting good inductance. And the idea is that over here, my chip is glued to this package, and this might be a piece of plastic, right? What if this were actually conductive? And let's say the back of the package had a little window in it. So we call this, some people call this the paddle. And so the window, they would say it's an exposed paddle. In other words, if you look at the back of the package, there's a little hole. If that were the case, then I could basically bond my chip to a conductor and have a bond wire that just goes directly down. This is called a down bond, as opposed to this long bond wire that goes into the package lead. And if they have an exposed paddle, then I can solder this paddle to the board ground plane. And now I have a much lower inductance path to ground. Okay? And that's also a pretty common way to reduce the inductance. Now, if you're being really aggressive, what can you do to reduce the inductance even more with an exposed paddle? Give you a hint. You want to make this bond wire as short as possible. Okay, I see people making gestures, but no words are coming out. Flip the chip upside down. Okay, that's the flip chip. Okay, let's not go there. Let's say the same simplistic technology. What's that? Put a via through the substrate? Okay. There are, in silicon technology, you can put vias all the way through the substrate, but it's not common. It's not common at all. Something simpler.
You thin your substrate.
Yeah, exactly. You just thin your substrate. So initially your chip is about 700 microns thick or close to a millimeter. You can just grind it down and make it very thin. You can thin it down to tens to hundreds of microns, and then that means that this bond wire is going to be extremely short. A very cheap way of reducing that bond wire inductance. Okay? So any questions about packaging? Packaging is extremely important for power amplifiers, and we're just touching upon the issue here. In reality, if you're going to design a power amplifier, you really should spend as much time on the package as you do on the actual circuit design, because not only are the electrical properties of the package important, but also the thermal properties. So all the heat that you dissipate in your transistor has to be removed essentially through the package. In fact, that's one of the disadvantages of flip chip, because here if you look, silicon's a pretty good thermal conductor, and so I can remove heat from the bottom of this chip onto the board ground plane, which is acting like a good, let's say, thermal ground. Over here though, because I flipped the chip around, the heat now can't escape through the silicon, because over here there is no thermal conductor. There's only air. So at best, if I have a fan, I've got some convection going on and I can remove some heat. But the rest of the heat has to get removed thermally through these bumps. And so instead of having the whole area of the silicon as your thermal resistor, it's going to be a low value, you have basically these thin bumps. And so the number of bumps in parallel, the area of those bumps determines the thermal conductivity, which could be much lower than you'd get here. That means your chip is going to run hotter for the same power consumption, right? Let's say your chip's consuming 3 watts. You basically multiply that by the thermal resistance to find the temperature increase over ambient. So the chip here is going to run hotter than the chip here. Okay? All right. Let's now switch to the next lecture. and we're going to look at some other classes of amplifiers. So up to now, we restricted ourselves to what we call linear amplifiers, Class A, Class B, and Class AB amplifiers. Actually, we just covered Class A so far. Yeah, okay. So, well, let's actually look in more detail at how much power we actually dissipate in our transistor. So the power dissipated in our transistor is instantaneous power, is just the current through the transistor times the voltage across its collector emitter, or drain to source. And in Class A operation, the current takes on this waveform, right? It's a constant plus a swing. And I can make this current perhaps as large as IQ. And the voltage swing is swinging symmetrically about VCC. Okay? So I just multiply this out, and I'm interested in the average power consumption. So I take the average, and if I take the average of this quantity here, I get 1/2. And so you see that the average power consumed by the transistor is the DC power, IQ times VCC, minus the power of the load. Okay, we didn't have to do any math. That's really obvious. This is conservation of energy. The DC power is the power consumed by the transistor plus the power going to the load. Okay? So one of the undesirable things, if we look at this expression, this is the average power consumed by our transistor. When is that maximized for a Class A operation? When there's actually no power being delivered to the load. So Class A has this undesirable property that when there's no input signal, you're just burning power for no reason, right? And it's only when there's a huge output signal that you minimize the power dissipation in the transistor. Okay? So that's really inconvenient, and it's summarized here that to the minimum power that you do burn in your transistor, which is IQ VCC over 2, only occurs when you're delivering the peak power to your load. Well, why is this such a bad thing? Well, if you are using a Class A amplifier, you're probably doing it because you want good linearity. In other words, you have a modulated waveform that has lots of amplitude variation. Okay? So if you plot the statistics for your signal, in other words, what's the probability that you're at a given voltage, it might look something like this. So here you can see that the peak voltage is V0, and or not the peak, the average voltage is V0, and with a very low probability, let's say it hits the peak value of VDD. Okay? Now because, let's say I don't want my amplifier to ever clip. I want it to always be able to deliver the right voltage at the load. That means that whatever the peak amplitude is, I have to back off from that peak all the way to the average amplitude, and the difference between the peak and the average may be several dB. Might be as worse as 17 dB in some applications, wireless LAN, OFDM modulation for instance. Or it might be just a few dB, 2 or 3 dB. Well, that's really bad because if I now calculate the actual efficiency of my PA, it's not 50% that we calculated last lecture. It's never going to be 50% to start out with. It's going to be something more like 30% when you actually build it. But it's actually going to be much worse than that because the efficiency drops as the output power decreases. So the average efficiency you may end up with is as low as, let's say, 6%. Okay? So this is one really undesirable property of Class A amplifiers, and we'll come back to this. The other issue is that up to now we kind of just talked about designing a PA, just the output stage. We focused attention on the output stage. But in reality, the amount of gain that you can get in one stage is maybe 10, 15 dB power gain. So if you want a PA with a substantial amount of gain, let's say 30 dB, that means multi-stage design. And the design of each stage that drives your PA is kind of like the design of another mini PA, because your gain is, let's say you're designing a 1 watt PA, that means that the stage driving the output might have to deliver up to 100 milliwatts. Well, I can tell you right now, 100 milliwatt PA is also a challenging problem. Maybe the first stage is not so bad, it's just 10 milliwatts. But the point is that when you're designing a PA, You really have to spend a lot of time designing the driver stages. Good news is you can be sloppy because the efficiency, the overall efficiency contribution from the driver stages is basically divided by the gain you see in front. So if you have a gain of 10 here and the efficiency of this thing is only 30%, it's only about a 3% hit on the overall efficiency. So in some circles, 3% is a lot, right? If you're talking to PA designers, they might spend 2 weeks on their design to get 3%. So if you're sloppy and you add another 3%, they might get very upset at you. In other circles, 3% is not so bad. So here's an example of a two-stage amplifier. So you have your output stage, you spend all this time, you get it to work, you get the voltage swing here maximized, design your matching network to deliver that power to your load, and you bias this transistor up at the right operating point, and now you need to drive it. Okay? And if this is a large transistor, you find that has a lot of capacitance, and so definitely you're going to have to absorb that capacitance into your matching network. And let's say in this particular example that the resistance, the real part of the impedance looking in, is less than the optimal impedance that you need for this driver stage. Same analysis that we did for the output stage applies to the driver stage. The driver stage, to have peak efficiency, should also see a voltage swing of VDD at this point, right, and a current swing as close as possible to the bias current. That means that, so let me come on the paper here. So if we have our output stage, let's say this is about a volt. So let's say you're swinging about a volt here. And let's say this has a voltage gain of roughly 10, just to keep things simple. So this voltage swing here is 100 millivolts, right? So if I now drive this with a driver stage, and let's say this is just a large capacitor, so it's just a coupling capacitor, that means that this swing here is only 100 millivolts. And if the supply is 1 volt, then the efficiency of this stage, right, is going to be 1/2 normalized voltage, normalized current. If the normalized voltage is 110, even before we look at the current, our efficiency is pretty crappy, right? It's 1/20. So clearly what I'd like to do is also swing 1 volt here. Naturally, the way to do that is with impedance matching. So instead of using a large capacitor, I can use a matching capacitor. I can make this CM and swing instead something on the order of a volt here. And now this driver stage also operates at peak efficiency. Okay? So matching, interstage matching is also very important when you design power amplifiers. Okay? Any questions about that? Pretty clear to everybody? Okay. Let's switch back to the slides. Alright, so the world does not end at Class A amplifiers. In fact, there's a whole family of classes of amplifiers, more than you probably want to learn about. Class B amplifiers, it's probably better to explain it on paper. So the idea of a Class B amplifier is I'm going to take an amplifier and bias it. Can we switch to paper? Thanks. I'm going to bias it right around the threshold of the device. Okay? I'll use a MOSFET to make the discussion simple. And then I'm going to drive it with a sinusoid. Because this is biased right around the threshold, if I look at the drain current, when the input is positive, it'll approximately be a sinusoidal pulse, but when the input goes negative, the device is cut off. So it will only deliver a half pulse like this, right? Well, what if I had another device also grounded like this, also biased up at the same point, but driven with the opposite polarity? So that means that when the input is positive here, the input is negative here, so this device is cut off. But when the input goes positive here, this device turns on, and it delivers the drain current here also delivers a nice half sinusoidal pulse. Well, what can I do? If I could patch these together, if I could somehow add them, I'd invert this one, and then add it here, then I would have my sinusoid back. Okay? Now, what's the advantage of doing this? Well, the advantage of doing this is if I look at my transistor again, and if I plot, let's say it sees some effective load. When the input is maximum, the current is high, which means the voltage is low. So if I assume that the output voltage is sinusoidal, it looks something like this. So this is, let's say, okay, I'll just make it simple. It doesn't really matter. So if this is the voltage, let's say VCE, the current looks something like this. Current is 0 during this cycle, and it's positive during this cycle. Right? So when the current is increasing, the voltage at the drain here is decreasing, right? So this is VDS, sorry. And this is I drain, which means that because I turn the device off during this period, when the voltage is maximum, I don't consume power during this half cycle because the current is 0. And I do consume power, so this is 0 volts. I consume power when the voltage is relatively low. So this is kind of the best time to turn on my transistor. It would be really stupid to turn it on here because I would dissipate a lot of power in the transistor. This is the best time to turn on my transistor, right? So I'm only turning on the transistor at the optimum time. I do the same thing with the second transistor, and then I add up their currents to get back the original current waveform. Okay? Does that make sense? Alright, so let's look at the slide again. Now the slide will make a little bit more sense. So here's those two transistors. I bias them through the secondary of this balun. This balun converts this input voltage into a positive voltage across here and a negative voltage across here. So this automatically performs that inversion that we talked about. And then remember, I need to take the current from here and add it to a flipped version of the current from this branch. Again, the balun does that nicely. So the balun will take this current and sum it with the negative of this current. So the load will see that full sinusoidal current waveform. Okay? So here is a plot of the current and voltages that I would get. First, the voltage. The voltage is sinusoidal. Basically, the current sinusoidal, so the voltage is going to be sinusoidal, but even if it weren't, I could put a tank here and force it to be sinusoidal. So for now, just ignore the tank. So I have a sinusoidal voltage swing, and these are the current. This is the current through one of the transistors. So it turns on when the voltage is minimum, and then it's off, and then on again and off again. So the product of this times this is the power dissipated in the transistor, and you can see now it's much smaller than it would have been if we had turned on the transistor here. Right. So this is the basic idea of the Class B operation. Okay. So let's calculate the efficiency of this Class B operation. Well, for each transistor, what's the average current that flows through it? Well, it's biased at the peak of threshold, so the only current that goes through it is when the input sinusoid forces it to make 1/2 sinusoidal pulse. That means that the average value of the current is just basically the average value of a 1/2 sinusoidal pulse, which is 1/pi times its peak value. Okay? So if we now calculate the efficiency of each sub-PA, right, we have two of them in parallel, because of symmetry, I can just calculate one, and that's the efficiency of the overall system. So by the same argument that we made before, the efficiency is 1/2 current swing times voltage swing, normalized. Normalized current swing is basically the peak current divided by 2 divided by IQ, and I can now substitute IQ as IP over pi, and the peak voltage swing, just like before, is again VCC. So plugging in that IQ is IP over pi, I get 1/2 times pi over 4, pi over 2, which gives me an efficiency of pi over 4, which is about 78%. That's great. Remember, the peak efficiency of class A was 50%. So this amplifier, right off the bat, is giving us a much higher efficiency. And you know, these theoretical efficiency numbers, you take them when you get them, because when you actually build a PA, you're going to lose a lot of that efficiency. So the higher you start, the better. The other thing which you may notice, if you're observant, is that the efficiency kind of scales gracefully with IP versus IQ. In other words, as I reduce the amount of power, the peak current basically scales, and the efficiency scales proportional to this ratio. That means my efficiency drop is linear with power. Okay, I'll come back to that. Okay, no, here it is. So if I look at the efficiency versus voltage, at VCC I'm starting out at 78%. And as I scale the voltage down, the efficiency is dropping linearly. On the other hand, if you do the same analysis for class A, the efficiency drops like V squared. So not only do I start off at a better point, but my efficiency drop is more graceful. Okay? One more comment about class B. So you might say, okay, you've got all these advantages, but you had to play some tricks. You needed 2 transformers, right? And you've got to somehow make sure that balance is maintained in the circuit, and you've got to add up these half pulses together. That may bother you. What if your timing is just a little bit off? You're not going to get a perfect reconstruction of the sinusoid. And many times in this class we've talked about transformers. Transformers are a pain, they're bulky, they don't have good high frequency performance. Well, it turns out that if you take a microwave circuits course, there are better ways of building transformers at high frequency. So this approach, you don't have to throw it out the window. You can still do it. But they also tend to be rather bulky. So the power, if we call this a power combining network, it will also be quite bulky, even at high frequencies. Okay, so can we get rid of that transformer? And the answer is yes. You can design a Class B amplifier. It looks a lot like a Class A amplifier, but the operation now is, it's critical for this circuit to have this LC tank. Okay? Can anyone tell me why I have to have this LC tank in the circuit? That's right. So if you go back and look what we're doing, let's go to paper. So going back to paper, thanks. I have an LC tank here, and this transistor is just delivering half pulses like this. It's not delivering this portion. So if this were to flow into the load, this is what the voltage at the load would look like. That's not what I want. I want the voltage at the load to be sinusoidal. So I use an LC tank to pick up that fundamental. So what's happening is the current harmonics are getting shunted to ground through this capacitance. Okay, so this is performing some filtering function for me. It's actually more fundamental than that. What this tank is doing is it's storing enough energy so that at the output, when the voltage swing needs to go negative, the energy stored in this tank is used and delivered to the antenna. So the pulse is now completed by the tank. All right? A very good analogy for this is imagine being on a swing, right? If someone is pushing you on a swing, they only need to push in one direction. for you to swing back and forth, right? They don't need to push in this direction and then also push in that direction. Why is that? Because a swing is a resonant circuit, right? It's a second order system, just like this. And if the quality factor is bigger than 1, that means that you're going to swing more than once before you stop, right? So similar thing here. The transistor is kind of like the father pushing his son on the swing, and he only pushes in one direction, provided that it's a good swing. Okay? So, in fact, this is exactly what we're going to do with this circuit here. We're going to bias this up again at the threshold of conduction, drive it with a sinusoidal pulse, and then let those current pulses deliver fundamental to the load and harmonics to ground. So let's do the calculation for the efficiency. A calculation is trivial. We've already calculated what the DC value of the current is. It's just the peak current divided by pi. And so to find the power that goes into the load, assuming all the harmonics are terminated to ground perfectly, then we just find the fundamental component of this waveform. Well, the waveform is a half pulse, so we integrate from 0 to pi and multiply, in fact, sine theta by sine theta, which gives us that the fundamental component is the peak current divided by 2. Okay? Is that clear to everybody? So if on the final exam, if I give you guys a PA with a quarter pulse, can you find the efficiency? Sure, it's easy. All right, so here's what the current and voltage waveforms look like. Again, very similar to before. The voltage at the collector, because the collector voltage is just the output voltage, right, shifted by this DC voltage. So this is swinging about 0 volts. That means that this point is swinging about VCC. It's charged up by this capacitor. So the output swings about VCC, and the current, again, I get these current pulses when the output voltage is low. And that means that plugging in the numbers, the efficiency is the same as the transformer version of this device. Same efficiency, 78%. And the only difference between this PA and the transformer one is that now the total power is delivered by one transistor. In the transformer case, half the power is delivered by each transistor. So I'm putting twice as much stress on one device, if you like, power stress. So this transistor is going to run much hotter. So the transformer idea is not all that bad. It lets us actually distribute the power a little bit and use the transformer as a power combining element. Okay, any questions? Yes.
Could you explain again why it's the same efficiency? Because it looks as though you have half the gain, and half the gain is going to other harmonics, so you're losing half the gain.
Okay, so let's look at why the efficiency is the same. So I have a single transistor, and so this is the average value, so this is the peak value, right? So the average value is IP over pi, right? And the fundamental component is 1/2 of the peak, right? In the other case, so actually let me draw it better. It's almost the same exact thing. Let's take the differential half circuit. So this half circuit consumes same average current, right, and delivers the same peak current. The only difference is that because I have two of them, right, I sum the powers at the output. So if you think about this from a half circuit perspective, they're more or less identical. Yeah, it's a little bit hard to explain with this picture, but you can convince yourself that this is the right answer. Okay, so now let's generalize this discussion a little bit. And the way we do that is, on this slide here, we kind of think about the difference between class A and class B. Class A, the transistor's on the whole time. Class B, the transistor's on half the time. And we saw things got better. So why not turn on the transistor even less amount of time, right? So instead of having a 180-degree conduction angle being half the time, let's make it 50 degrees or 30 degrees or 10 degrees. Do things get better, right? And so any amplifier that has a conduction angle below 180 degrees is just called a class C amplifier. Okay? So it's a whole family of amplifiers. The one, before we get into class C amplifiers, I should say that almost nobody builds pure class B amplifiers. Okay. Why is that? Yeah, there's a dead zone, or what some people call crossover distortion. Problem is that you have to get the slide, the paper. Yeah, so you have to turn this transistor on and off, and there is basically turning a transistor on is not easy, especially at high frequency. You have to charge up the base. You have to put in enough base charge to support a current. There's a finite charging and discharging time. It's really ugly to turn a transistor on and off. It's much better to keep the transistor running all the time. You know, instead of biasing it at zero, let's say my average current swing is 100 milliamps. Why not run 5 milliamps of current in here? That'll have a negligible impact on my efficiency, but at least it always keeps my transistor on, and I never have to completely discharge the base. So you say, okay, discharging the base, what's the big deal? Well, not only is it slow, but it also introduces distortion. So if I keep some current running through this device and I avoid transitioning into the cutoff state, I actually will get much better distortion out of this device. So almost every real Class B amplifier is called a Class AB amplifier. Class AB because it's not really Class A. It has current flowing all the time, but it's really little current. It's more like Class B. The efficiency is going to be much closer to Class B. So instead of 78%, maybe it's 76%. Really, it's not a huge difference from Class B operation. If you implement this Class B amplifier using transformers, there's another problem, and that's that there's a region where basically neither transistor is on. So if you actually built this thing, you'd have basically what's called the dead zone, and this will introduce distortion. In fact, if you build an audio amplifier using this technique, this is really ugly. You can hear this because this has lots of high frequency components in it. So you put in a pure tone and you hear this high frequency distortion. People call this crossover distortion. Because it happens when the signal is crossing zero. Okay. Now, solution, of course, is just trickle some current through your device and you get rid of this problem. All right, back to the slides. So the idea now is if I decrease the time over which my transistor is on, I would expect my efficiency to get better and better. So here, again, this is a sinusoidal voltage. The voltage swing is the same, but I've reduced the conduction angle. In fact, what I've done is I'm trying to turn my collector current into a pulse, a very narrow pulse. The more narrow it is, the less power it'll consume. Ideally, if it's a perfectly narrow pulse, again, this picture is not so good, so let's look at it over here. If it's a ideal pulse, so here's that waveform, I'd like to turn on my pulse right there, because at this point, the voltage across the device is zero, or nearly zero, and so there'll be no power dissipation in the device. As opposed to a pulse like that, a big fat pulse, there's going to be power dissipation all over here. Okay? But the caveat is that to deliver the same amount of power, right, the integral should be constant. So that means that this pulse has to get taller and taller. And as it approaches just a point, it becomes a delta function. So the best PA you can design would just deliver delta functions to your load. Of course, perfectly timed to correspond to the minimum point. Now, obviously, that's going to be pretty hard to do, right? Delta function, what are the harmonics of a delta function, right? They equal the signal itself. So you need a transistor that can produce all these harmonics, and somehow, not only is it going to produce harmonics, very strong harmonics, but all these harmonics are going to terminate into our capacitor load. There are no perfect capacitors. Capacitor load is going to have some finite Q, so you will dissipate power in your harmonics as well. Not to mention that it's very difficult to make a transistor that can put out very narrow pulses. So great theory, in practice, pretty hard to implement. Well, how would you implement it in practice? One way to do it is you just take the exact same amplifier as our class B. This is one of the few instances in this class where I could just copy and paste a figure and just change the text around, and just bias it at a threshold voltage, basically below your threshold voltage. That means that this transistor will turn on for conduction angle less than 180 degrees, right? Depending on how far we put it below threshold, it'll... So here, let's draw a picture. Actually, I think I have a good picture here. Yeah, where's that good picture? All right, I guess I'll have to draw it. So let's say this is the input voltage. And let's say I bias my device somewhere around here. Okay? That means that the input voltage, actually I drew it wrong. I have to bias it somewhere around here. So that means the input voltage has to get this high for it to turn on. So this is going to be my conduction angle, right? If I bias it right at threshold, it would be right in the middle. Conduction angle would be 180 degrees. If I bias it over here, then the conduction angle gets narrower and narrower. And so you can play this game of biasing it very close to the peak of your input voltage so that it just turns on for a very small amount of time. Okay? All right, so what's the problem with doing this? Well, one of the biggest problems is that Class C amplifiers are actually very nonlinear. The reason is that if you actually look at the relationship between the fundamental of your current with the input voltage, they're no longer linearly related. They're nonlinearly related. And we'll do a derivation and show that. Which means that it's now by definition not a linear amplifier, right? Forget small signal linearity, right? In this at this point we're talking about PAs. Nothing's a small signal. So there's no linear relationship between the input voltage and the output voltage, which means it's going to generate a crazy amount of distortion. There are applications where we can still use this PA, namely anytime we use a modulation scheme that does not change the envelope or the amplitude of our signal. For instance, FM, right? Frequency modulation, what you listen to on your radio. All the information is embedded in the phase of the signal. So I can modulate the frequency, and that's my information. In fact, the input of an FM receiver is a bunch of limiters. Get rid of any extraneous amplitude variation that you may have picked up due to, say, multipath. In a digital communication scheme, I just put my constellation points on a circle. And so this might be a phase shift keying system where I can transmit any one of these phases, and that corresponds to a different digital bit. And I can either move instantaneously from one phase to another, or I can move smoothly. All host of modulation schemes invented around smoothly moving back and forth between these constellation points. The reason I like to do it smoothly is because if you change the phase abruptly and you filter your waveform, you introduce amplitude variation on the waveform. If you do it smoothly, you will not introduce amplitude variation after filtering. So in these kinds of applications, you can use a linear amplifier. So what's the disadvantage of using a a modulation scheme that's constant envelope. Okay, Christian?
To increase the number of bits, or the number of bits you have to increase your power to increase the radius of the circle?
That's part of it. How else could we say that? Yeah. That's right. The spectral efficiency of the system is quite low. And by spectral efficiency, we mean basically you have some kind of bandwidth. Let's talk about analog systems because it's easier to explain. So what's the sensitivity of your human ear? How many kilohertz can we hear? Okay, at most 20, right? Dogs can hear more than that, but humans, it's more like 10 kilohertz. If I use a AM system, that means that in 10 kilohertz I can put basically one channel of information. If I use FM though, the bandwidth required is much larger. It takes roughly 10 times more bandwidth to encode that same amount of information. So next time you're on your radio dial, notice that how closely spaced AM stations are versus FM stations. FM stations are much further apart than the information they contain. That's because the modulation scheme is inefficient. Now the advantage of FM is that it's very insensitive to any kind of amplitude noise, so it sounds a lot better. Okay? But you've paid a price. You've paid a price, you've given up bandwidth to get better sensitivity. Now, in digital modulation schemes, the way we characterize spectral efficiency is how many bits per hertz of bandwidth can you pack. So if one modulation scheme can pack 2 bits per hertz and another one can pack 10 bits per hertz, certainly the one with 10 bits per hertz is more efficient. And so if I basically go back to this picture here, let's say I just want to pack as many bits as I can into, so this big rectangle is the maximum power that I can transmit, right? The amplitude here, it corresponds to the power, v squared. So if I'm constrained to be on a circle, I can only populate points on the circle. But all of a sudden, if you allow amplitude variation, I can populate points all over the place. So I can pack a lot more bits into my constellation. And now you can see that these vectors have different lengths, and so depending on what symbol I want to transmit, my amplitude is going to vary. So the original waveform, which was constant envelope, the phase changes, but the amplitude is constant. Now the amplitude and the phase are changing in some complicated fashion. And if I want to now put this through an antenna, I need a PA, and that PA better preserve these amplitude variations, because these amplitude variations contain information. Okay? So class C is okay for this, not okay for that. Okay. So how do you improve a class C amplifier? How do you actually impart amplitude information? A very good example is, again, radio. If you're transmitting information on a radio, the transmitter is actually a lot of power, right? Let's say you have an AM station, and let's say it happens to be a 10 kilowatt station, right? If the efficiency, if you have to use class A and your efficiency is, let's say, only 20%, that means you're going to burn 5 times as much power. Your power bill is going to be 5 times as expensive as it needs to be. If you use class C, you can maybe maximize your efficiency, minimize your power bill, but no one's going to understand anything that you're saying because of distortion. So the solution is actually a combination, which is called collector modulation. And the idea is that if I actually run this class C PA in saturation, so that every time I put in a signal, it just rails, then the output power will be a function of the supply voltage, because it's railing. If I vary the supply voltage, then I can impart amplitude information on my load. So what I do is I take my general modulated waveform, which contains amplitude modulation and phase modulation, I remove the amplitude modulation and only apply phase modulation to the class C amplifier, and then I take the amplitude modulation and I go through another PA and apply that to the collector of the device. Now, you might say, you've doubled the problem. You've got to design another PA, and this PA now needs to be linear, right? Well, it turns out that designing this PA is much easier than designing this PA. Why is that? Yeah, the amplitude information has been stripped of the carrier. Carrier might be at a gigahertz. The amplitude information might be kilohertz or megahertz. So this is a very low frequency PA design, and there's a whole class of techniques such as switching power amplifiers that we'll discuss that are extremely linear and extremely efficient. All right, so that's collector modulation. Any questions about that?
Extremely efficient. So how efficient?
So a Class C amplifier in practice will have an efficiency 50 to 60% at best. At best. More realistically, 40%. Okay? All right, so another trick to improve the efficiency, let's say of a Class B amplifier. So let's go back to paper here. And remember, in a Class B amplifier, we have a half pulse going like this, and we turned on the pulse when the voltage basically is minimum. Well, I could improve the efficiency if I could somehow change the voltage waveform. So instead of having a sinusoidal waveform, I could somehow, let's say, add some harmonics to it to make it look more like a square wave. So if this is my voltage waveform and this is my current, you can see that here I'm consuming this power, here I'm consuming that power. Clearly, this is going to be more efficient than that. So the question is, how can I square up the collector voltage waveform, right? So that's the idea of a Class F amplifier. If you take away, for a moment, forget about this circuit here, this resonance circuit. If you just directly connect this point to here, let's say through a coupling capacitor, then the voltage at this drain is constrained to be sinusoidal because it's connected to a tank. So what I need to do is somehow isolate the drain here from the tank at the desired harmonic. So for instance, if I want to add a third harmonic to my voltage waveform, I make a tank, parallel tank, that resonates at third harmonic. Now at third harmonic, the drain basically sees effectively a very high impedance looking to the right, and it sees whatever is basically connected to the drain. So what I can do now is take advantage of that third harmonic generated by the transistor and make the voltage of the third harmonic equal to some optimal value. Okay? If you do the math, again, it's all mathematics, you find that the best value of the third harmonic you can add can change the efficiency from 78% to 88%, so about a 10% boost. It's pretty good. Just a couple of elements and I've boosted my efficiency. You can see that it doesn't interfere too much with the fundamental, because at the fundamental frequency, this inductor acts like a short circuit. Okay? And so you say, well, that was a nice trick. Why not add some fifth harmonic, right? So I put another tank in series here with a fifth harmonic. And now I can add a little bit of fifth harmonic and play around with that fifth harmonic and try to optimize the waveform. It's actually beyond, let's say, fifth. You definitely don't want to go to seventh because it's diminishing returns. You know, there's a good mathematical proof for it. You guys all know that the convergence of the Fourier series to a perfect square wave is not very good, right? It's a very slow convergence. So, you know, adding third helps, adding fifth helps even less. You pretty much stop there, because now you've got two series elements in series with your tank, and there's going to be some loss going through them. But certainly doing this is a good way. There's even a better way to do it. The better way to do it is forget about adding tanks, just add a transmission line. Okay? So if I have a transmission line that's quarter wavelength, that means that at any odd multiple of a quarter wavelength, it takes a short circuit and transforms it to an open circuit, right? In this case, I don't have a short, I have a low impedance. It transforms this low impedance into a high impedance, or high reactance, really. So if I make this circuit be a quarter wavelength at third harmonic, automatically it'll also be a multiple of a quarter wavelength at all odd harmonics. So it'll be at fifth, at seventh, at ninth. So automatically this transmission line will decouple this circuit from the load at all harmonics above 3, all odd harmonics above 3. And that's perfect. That's exactly what we want. So in theory, we can design this so it sees a square wave because we've got all the harmonics there. So in theory, I can approach 100%. Practice, of course, things aren't so simple. Okay, so let's transition now and talk about a different style of PA, what we call switching PAs. So up to now, we've kind of been using our transistors as amplifiers. At least we've pretended that they were amplifiers. What if we just give up that notion? What if we just say, forget it? Like a MOS transistor, it's just a damn good switch. Let's use it as a switch. Why bother trying to use it as an amplifier? You know, all these process engineers are out there optimizing its performance as a switch. I should design a PA that uses my device as a switch. So that's the philosophy behind switching amplifiers. Simplest incarnation is something like this. I have a supply and a ground, and I switch my load between supply and ground. Right? It's a square wave. Well, I don't want that square wave to go into my antenna, so I just put a filter on there and only allow the first harmonic to flow into my load. So I convert, basically this converts DC power into AC power using switches. What's the efficiency? Well, if these are perfect switches, the efficiency is 100%. Switches don't consume power because the switch, when it's on, has 0 volts across it. It can support any current that you like. When it's off, it has no current through it, so it could support any voltage that you like. And in either case, it doesn't dissipate any power. Well, how do I control the amplitude? Right? The amplitude is just going to be dependent on VDD. So I can play a few tricks. I can supply modulate just like we did in a Class C amplifier, or I could actually modulate the amount of time that these switches are on. If I do that, I can also impart amplitude information onto the load. So we'll talk about that second technique in a couple of slides. No surprise, this is how you might build a Class D amplifier. It's just an inverter, right? And because now you're using a real MOS, not a switch, an ideal switch, obviously the on resistance is going to hurt you. You want to make your switch as big as possible, right? The bigger the better. No, because if you make it too big, it's going to have too much capacitance, and then it's going to be a bad switch when it's off. Also, that capacitance is a parasitic capacitance, and since you're turning the switch on and off, you have to charge and discharge that capacitance. That means that there's going to be energy associated with charging and discharging that capacitance, right? The energy is CV squared, and just like in digital circuits, you're going to burn switching power CV squared F. Not only at the outputs, but also at the input. These are huge devices. Their gate oxide capacitance is going to be huge, and so you're going to have to drive a huge amount of power into these switches. Well, you could make this a resonant driver, right? You can tune out the capacitance with an inductor, but if you calculate the value of inductor you would need, it would be ridiculously small because these switches are so big. So you might need a very tiny inductor, and even if you manage to do it, you're only going to bring the power down by the Q of the circuit. And because that inductor quality factor is going to be 5 or 10 or whatever, you might have a 1/5 or 1/10 reduction in the power, but it's still going to be significant. Also, because these MOSFETs have finite on resistance, when you push a lot of current through them, you will dissipate a significant amount of power, right? I squared times R. So when you really design this thing, you find that it's pretty efficient. It's pretty good. You could get 80%, 85%, but that's at low frequency. As you go to higher and higher frequencies, those switching losses really come into play and push the efficiency below 50%. Okay. Here's the waveforms. Again, it's pretty obvious. The drain voltage is just a square wave. and the current through each device is going to be a sinusoidal pulse. And since the pulse is off when the current is on, voltage is on, and vice versa, ideally no dissipation in the switch. In reality, the voltage is not going to be zero here. It's going to be the current times the resistance of the switch. So you can calculate. It's a good problem for the final. If you have some switch resistance, what's the efficiency? Okay. It's so obvious you don't need to do it, but if you like to write a few lines of algebra, you can calculate the efficiency and prove to yourself that is indeed 100%. Okay, so we'll skip that. All right, I think I talked about all these loss mechanisms, so I'll skip ahead. I'm not going to cover it in this class, but there is a better version of a switching amplifier, and it's a Class E amplifier. Okay, so Class D, Class E. And the Class E amplifier, the advantage of it is that it can absorb the capacitance of the switch into your load network. And so you can actually build Class E amplifiers with very good efficiency. Now, again, going back to the question that was asked earlier, people have demonstrated above like 95% efficiency in Class E amplifiers at lower frequencies. At RF frequencies using, let's say, CMOS, actually a student at Berkeley a few years back, Martin Zai, demonstrated efficiency better than 50%, delivering 1 watt of power using conventional CMOS technology. That's an impressive achievement. It was definitely a first CMOS PA capable of 1 watt of power and still maintaining good efficiency. And it's an area that's still active in research. Okay, so I'm not going to talk about that in this class, but be aware of it. Might be on the final. Just kidding. All right, another class, somehow people just decided to skip all the way to Class S. What about all the letters in between? Yeah, this is the Mercedes of PAs. The idea is that I'm going to convert amplitude information into phase information or into timing information. Again, the philosophy is that digital circuits are good at switching and they're good at timing. So I can design really basically a pulse width here that's proportional to the amplitude. Of course, the pulse repetition rate better be much higher than the signal rate, right? The RF signal rate. But as long as I can satisfy that condition, then I can very accurately convey amplitude information with pulses, and then because now this is just a phase modulated signal, I can push this into my Class D amplifier or my Class E amplifier and get really good efficiency. It's practical for low frequencies, right? Not practical at gigahertz frequencies, because if it's gigahertz, your switching rate would need to be like 10 gigahertz, right? That's pretty hard to do. The other thing that makes it impractical is that you can imagine this is going to generate harmonics like crazy, right? So all those harmonics have to be somehow filtered out before they hit the antenna. So if you're putting this through a speaker and you filter it, maybe that's okay because no one can hear the harmonics anyway, except for the dogs running around. But if you're putting it on an antenna, clearly you have to worry about it because, other people are going to hear it too. So here's how you build a Class S amplifier, very trivial. I have this magic circuit that converts amplitude into pulse width information. Very easy to do that. It's just a ramp generator, right? A ramp generator and a comparator. Run that into, let's say, a Class D amplifier, filter the output, and you have yourself a PA with nearly 100% efficiency and very linear PA. This might be something you could use, for instance, for that low-frequency PA that we talked about in the collector modulation. Because the amplitude information is indeed at a much lower frequency, right? Your carrier is at a gigahertz, but your amplitude might be at a megahertz. So I can run this thing at, let's say, 20 megahertz and convey the amplitude information very accurately. You need to filter the heck out of it, though, because you don't want those harmonics to get into your PA. Now, I remember when I was young, almost all audio amplifiers were Class AB amplifiers. And it was a lot of fun to take them apart. You'd look inside and you'd see 4 transistors, 4 big transistors with lots of heat sinks on them. You see these big transformers, big, huge, heavy transformers, because this is low frequencies, right? So you need a huge transformer And those were those two transformers that we showed you to do the power combining, let's say in a Class B amplifier. And, so good PAs were very heavy. They're very big. They got really hot. They burned a lot of power. We're talking about kilowatts of power here, right? You're going to throw a nice party. You need lots of, audio power. Well, today you go and buy a PA, and all of a sudden there's no transformer. It's light and sounds pretty good. If you look at the harmonic distortion, it sounds pretty good. What's going on? Well, what's going on is this. This is what the PAs look like now. They're no longer Class AB. They're Class S or Class D with some kind of sophisticated digital signal processing to convert amplitude information into timing information. A lot of them are like sigma deltas, if you're familiar with sigma delta converters. So these kinds of PAs have more or less taken over the world up to a certain frequency. There are people out there who are trying to make this stuff work at RF, because if you can make this work at RF, all of a sudden you've solved one of the key problems in power amplifier design: how to achieve efficiency and linearity simultaneously. It's a very difficult problem. Okay, I think we'll stop it there. Any questions? Yes.
Also, there's a low Pascal to rise remove harmonics. But if you have a perfect square wave, don't you lose a lot of energy of the harmonics?
No, because you're not putting those harmonics into a real load. You're just putting it into a capacitor. Okay. Any other questions? Okay, so make sure you check the website for announcements, and I'll ask Al to also email you guys and funnel them through me. By the way, has everyone received a copy of last year's final? Okay, good. All right.
Is it also on the web?
No, it's not on the web. All right.